I'm a research assistant, and I do that part-time alongside my PhD. My PhD is part sponsored by Proteus because it looks at fluorescence-based monitoring of E. coli, which ties in really well with some of the work we do with our clients. And I'm part sponsored by Proteus Instruments and the University of Birmingham. So what I'm doing in that sort of feeds directly back into my work here. And that can involve all sorts of things, from sort of writing reports and writing website content. I also do sort of data analysis as needed. And I get to have a look at a lot of the projects that are going on, which is quite an exciting place to be.
So you do fluorescent. So does that? So from what I've been overhearing, is fluorescence is used to help measure the toxicity of water? Is it?
Sort of. So what we work out is that fluorescence can be used as an organic matter proxy. Because we know that certain groupings of organic matter fluoresce on particular wavelengths. So what we can do now is target specific wavelengths and see if what we think might be there is there. So we use two main wavelengths here, tryptophan light fluorescence, and we also use one that's sort of colloquially referred to as CDOM. And tryptophan, for example, it's tryptophan light fluorescence. Tryptophan's an amino acid, and we can use it as a proxy for something like BOD or COD and coliforms, which then comes onto like E. coli and things like that. And the application of that is then seeing whether we can have a real-time diagnostic tool for something like drinking water or bathing water to know instantly or not whether the water is being contaminated with something like sewage.
Okay, so it's literally... that's really smart. So obviously if it fluoresces, it's on the UV wavelength, somewhere on the wavelength. And I'm guessing certain sort of bugs would fluoresce the same way that certain colours reflect back.
Yeah, so it's basically, we fire what we call the excitation wavelength at it, which is what we know it should start to excite. And then basically the electrons start to move up in their energy levels, and to get back down to their ground state, they have to emit a photon, because in these particular groupings, it's I'm paraphrasing a bit, but it's the easiest way for them to return to their ground state is to emit a photon. And we know on what wavelength, if it's what we think it is, that should come back at. So we have a detector, and that detects what's emitted back. E. coli is sort of very closely related to tryptophan light fluorescence. There's been a proven relationship between the two because E. coli possesses tryptophan and another compound called indole, which fluoresces in the same way. It's not exact. We can't detect sort of the minimum detection limit across the field. You can't go down to 0 and 1, but it's a very good indication. And what we're working on at the minute is getting that detection limit down, because if you're talking about drinking water, you've got to know the difference between no, there's no contamination, and yes, there's one coliform, and therefore it has been contaminated.
Okay, and what's the difference between like fluorescing and like reflecting or like refracting?
Just different processes. So fluorescing and phosphorescence, which you've probably heard of, which normally phosphorescence you will see. It's just a different process because this involves sort of electron movement.
Is it generated by the actual exciting the sort of how would you refer to it? Like E. coli, would you refer to that as a bug or as a...
It's a bacteria.
So as a bacteria, so it excites the bacteria?
Sort of, so it excites things the bacteria possesses. So tryptophan is, it's an intrinsic fluorophore, so we don't have to add anything to it to get it to fluoresce, it just does. Because of the electron arrangement and the fact that once they've increased, because the theory of electrons being sort of in shells, or energy levels would be more specific, around the outside of the molecule. And then, as you excite them, the energy of the electrons raises. But as we all know, the one rule of energy is it has to be transferred, can't be destroyed. And so as you're firing the excitation wavelength at it, the electrons move up. And then as you take that away, the electrons have to get back down to their ground state. They cannot remain there indefinitely. And that's where the photon gets emitted. And then hopefully we're standing there to detect it. And we're like, brilliant, it's been contaminated. Which is never normally a brilliant moment, but it is an odd kind of science where, you detect what is basically sewage or poop, and you think, yes, it works.
That's literally what the Proteus unit does in real time.
Yes.
So from my light reading on this, at the moment it takes a considerable amount of time for a measurement, for something to be measured and then to get data from that. Yeah,
so if we're looking at BOD and COD, so that's our biochemical oxygen demand, chemical oxygen demand, that's BOD is a 5-day test, and you cannot rush that. And that's 5 days once it gets to the lab, which you have to do within 24 hours. So then add another day either side for, transport and processing and emailing and all the rest of it. It's a long process. So if, for example, a lot of work we've done with, sewage treatment works, if there's been a spill and the BOD is what you're using to detect it, you won't know that until 5 days later.
And there could potentially be people swimming
in it. And the fact is also, just taking out the human element in terms of discharging sewage to an ecosystem or something going wrong and causing large amounts of sewage to be discharged, it's devastating. But that takes, it takes on time. Coliforms, there are quicker methods now of detecting them. There's still nothing that's instant. Most of them involve a lab, which means great if you have the facilities and the money to spend in that. But if you're in sort of disaster response scenario at the end of an earthquake, something like that, you're not going to have time to crack out the tubes and go to the lab and get it all sorted.
Keep the lava at bay for 5 days.
Yeah, just sort of say, everyone hold on while I run to the lab and check the water's safe. And okay, there are methods of analysing water quality on the spot, but what we're trying to do is get an increasingly better way of doing it.
That's really cool. And that's Proteus. Is it like a measure for margin of error in Proteus, or is it like really sort of high success rate for detecting?
As an indicator, it's really good. Like I said, what we're working on now is minimum detection, because fluorescence, the main problem is as you go down, because again, we're looking at wavelength groupings, but it doesn't mean that the one thing that's fluorescing is the only thing that's there. So there'll be other things on that wavelength. So then what we do in a lab scenario when we do the calibration is we take the fluorescence reading and compare it to one or two other methods of detecting the same thing and work out the calibration between them. Because fluorescence fingerprints, like the signature of the water, tryptophan can look a little different in one water source to how it presents in another. Sometimes you get interference in other wavelengths, so we'll use a second fluorometer to sort of help make it more specific. And that's really where the technology is going at the minute, because until about, I keep saying 10 years ago, but it's probably about 12 now because I've been saying it for 2 years. Until then, it was a case of you could only do this kind of analysis using a big desktop machine in a laboratory. And it would scan all the wavelengths, and we still use those machines, they're great, but obviously...
spectrometer?
Yes, a fluorescence spectrophotometer. And we've got 2 at the university, and they're great when you want a whole profile of the water. But it's no way to actually analyse anything in situ. So if you want to learn more about Proteus, we've got lots of information and case studies of how we've applied it in different environments, because I'm aware I've spoken a lot about drinking water, but lots of different environments at www.proteus-instruments.com.